Uh, Hello, colleagues. Let us start today's talk. Today, our external speaker is Yuke. Sorry if I'm pronouncing maybe incorrectly.
That's actually pretty good.
He's an assistant professor in the computer science department of UT Austin, where he directs the robot perception and learning lab. His research lies in the intersection of robotics, machine learning, and computer vision. He received his master's and PhD degrees from Stanford University. His research works have won several awards and nominations, including the Best Conference Paper Award in ICRA 2019, Outstanding Learning Paper at ICRA 2022, and Best Paper finalist in IROS 2019-2021. He is a recipient of the NSF Career Award and the Amazon Reward Awards. Yeah.
Okay. Yeah. Thanks for inviting me. That I thought it's interesting that I realized office is here because I used to live in walking distance from the office in the shadow apartment on the Shoreline Boulevard. So no wonder that I saw so many Nuro cars like back then in the 2090s before I moved to Texas. So yeah, and I'm excited to finally get a chance to visit the office. So today I will talk about the quest for compositional robot autonomy, and kind of sit here in this meeting. I kind of like the format is kind of cozy, so we can make it more discussion oriented. And I tend to give pause like a kind of like different chapters of the talk, but feel free to just interrupt and ask me questions. Okay, so just let's get started. And so if you are kind of following the news of the kind of a broader robotics world beyond autonomous driving, you might heard that there's some exciting development in the robotics world is coming from outer space, right? So this a big telescope, James Webb Space Telescope, that is supposed to be a replacement of the Hubble telescope, is now successfully launched and fully in operation. And to me, this is a remarkable feat of robotic system engineering. So out of there are 300,000 of different tasks to be done, and there are 300 of single point failure, meaning that if any of these 300 tasks fails, the entire telescope fails as a whole. And this is even more difficult problem than building a Nuro car, because you cannot send a technician to go on site and fix the robot once it's launched, right? It's in the outer space. And this is a ginormous effort. It costs like $9 billion task, and like a 20 years past effort. They're supposed to be launched in 2013, and they're kept delayed and procrastinating, and then eventually launched in the final week of 2021. But anyway, after this, and while receiving beautiful images from the telescope, and there's a lot more you can see, and it's absolutely amazing how it looks. And not only that, they are aesthetically pleasing, it's absolutely beautiful to look at, like as a outsider while not doing astronomy, but also this is going to be crucial for us to unlock our understanding of the universe to the next level, right? So this has great scientific value. So looking at this telescope kind of make me wonder that apparently we cannot figure out a way to build really complex robotic system that is highly reliable, even though there's so much like a system challenge. But why kind of the personal household robots, like our research focus on, as well as like a general purpose autonomous driving car, I'm talking about like say level 4, level 5, always seems to be 5-10 years away from now, right? So from social media and from news. So that's kind of my question. But of course, one of the key reasons is that we want to deploy this system in the wild, in general purpose environment. So there needs to be a generalist to handle all kinds of difficult situations. And to build this kind of a general purpose robotic system to handle this all kinds of various situations, and it's really hard or infeasible to manually program this robotic system, right? So to write down a Python, C++ program to specify the behavior. That's where machine learning and AI algorithm comes into picture, right? So now they offer a new paradigm to design robotic behavior that's otherwise hard to manually engineer. Typically, for robot learning and AI research, like what we are doing here showing the picture, it looks like this, that we just have a small group of students and researchers and professors together. We brainstorm some ideas on the whiteboard. We implement the models in PyTorch, TensorFlow, JAX, whatever libraries you like, and then got test that model on the real robot, right? And then if we get a decent success, say 70% success, and we beat all the baseline of our choice, we're pretty happy with that. And we go publish this paper in a top tier conference, and then we move on to the next one. It is very common that when we work on the next project, that we're not building on top of the previous one, right? So there's no really effort taken that moves this kind of 70% success model to the 99.999% performance guarantee we need for widespread deployment. So we see a dichotomy here. On one side, we know, like, using rigorous engineering principles, how can we build really sophisticated yet reliable robotic system like the James Webb Space Telescope. On the other hand, we have an emerging paradigm of designing robotic behaviors using machine learning, computer vision, modern AI tools. Naturally, we're asking, can we combine the best of both worlds? By that, I mean, can we combine the rigorous engineering principles that we have in this robotic system engineering, as well as this kind of modern data-driven tools together to build like adaptive and general purpose system, but also with robustness and the performance guarantee. So that's the kind of the central research questions like my research has been looking at. So in particular, as a machine learning researcher, I have been trying to draw a lot of inspirations from system engineering, right? So what do it take to build like scalable and robust systems? So in recent years, we have been looking at these two principles that we draw a lot of inspiration from, that is abstraction and composition, that is used in a lot of day-to-day practice in software engineering. What is abstraction? Abstraction concerns about the division of labor, right? So if I want to build a self-driving car, it's a very complex system, really hard computation problem. How can we break that down into smaller and individual pieces so that we can develop and conquer? And so the perception team go solve the perception problem, decision-making planning solve the planning problem, control team planning solve the control problem, so they don't have to mess with each other, so they can have reduce the problem size without solving autonomous driving in one shot. And then what is composition is concerns about like the harmony of labor. If we piece together this individual solutions, how can we make sure that this individual components work in coordination towards an overarching collective goal? So the question to be looking at is, how can we kind of incorporate the principles of abstraction and composition in building robot autonomy? So if you take a system perspective, looking at a robotic system, like let it be the manipulators or autonomous driving cars, we can think them as complex systems that sense and act, right? So the robot perceives the environment, receives sensory information from the external world, and it processes this information to make intelligent decisions and like the actions. And then the actions in turn interact with the environment to create new sensory stimuli for the next steps decision making. So there's a perception action loop going on, like so through the robot's interaction with the environment. And one kind of straightforward approach to model this perception action loop is a direction mapping, right? So you can imagine there's a policy pipe here that maps the sensory data received from the onboard sensor of the robot to the motor actions. And if you take a computational perspective, there was some kind of really complex nonlinear functions you can feed to map the sensory data to the motor action. And how can we feed a really complex nonlinear function? Deep neural network, right? So like a very deep network, and we can train with input and output supervised learning, boom. And that's so very often referred to as a pixel to torque approach, right? So we use this large black box network to feed the data directly from input to output pairs. And this has been a quite fashionable approach in the last few years for building robot autonomy, especially after seeing the success of deep learning in other AI disciplines like computer vision and natural language processing. People are thinking about the same paradigm for robotics. We have seen a lot of impressive demos and proof of concept using this approach, including autonomous driving and robotic manipulation. You might say examples like OpenAI doing the Rubik cube and like using dexterous hand, right? So that's a kind of like a very impressive showcase of what this end-to-end pixel to torque approach can take. But increasingly, we have seen more kind of shortcomings and limitations of this approach in terms of the high data requirement. It needs a huge amount of data to train and have low learning efficiency. It's not particularly good at learning from few mistakes or few samples. Also, because it is a big black box, it lacks the performance guarantees, or it lacks of the kind of interpretability we like when it for deployable system. So our research, instead like seeking this like a pixel to torque approach, we look at like how can we break that down into a modular yet highly coupled kind of autonomy stack. So I will first talk about how can we build state abstraction from sensory data, or also talk about how can we build action abstraction from low-level motor actions. And then once we have this two level of abstraction, now we can build more robust and generalizable decision-making modules on top of these two abstractions to achieve kind of high learning efficiency and the more kind of transparency and the robustness, which I call the compositional robot autonomy stack. So as a disclaimer here, today, a lot of talks you're going to see, a lot of works focus on the robotic manipulation domain with robot arms. But I would argue that a lot of the ideas are shared and actually transferable to autonomous driving. Actually, in the last, I'm going to close loop to show you some of our early work in applying the similar principles to the autonomous driving domain. Okay. So that's kind of today's roadmap, and there's two parts of the talk. I will first talk about learning actionable visual abstractions from interaction, reviewing three of the recent work, and then I will talk about like the second part is like how do we build behavior abstraction, action abstraction using skills, and we use those as the behavior building blocks to synthesize long-term robotic behavior for compositional task modeling. So let's start with the first one. I will talk about GIGA, Ditto, and the asset. So we'll first study object representation learning for robotic grasping. So why grasping? This is a essential, very important component of a lot of manipulation tasks in the real world, let it be logistics and you do pick and place, assembly, or smart warehousing. So we're in this case, the input is some partial point cloud observations of the workspace with a bunch of objects. And here we assume that we are doing open loop grasp. So all you need is to predict some 6-stop grasp parameters, like specify the target pose of the end effector. And so the 6-stop means like 3D positions of the gripper center and also the gripper orientation. So our intuition here is to reasonable grasp, and we need some 3D understanding to understand the 3D geometry of the thing, and also we need to understand like some actionable information, like affordance. By affordance, we mean the grasp likelihood of grasp success and also its corresponding grasp parameters. So our key insight is this affordance understanding and the geometry understanding. This seems to be two different like a 3D vision tasks, but they are in essence the two sides of the same coin, right? So like from kind of human cognition, we can argue what makes a mug, or how we perceive objects. So on one end, you can see that what makes a mug is because it looks like a mug, right? So it have this empty inside, have a curvy handle. So once we recognize this visual attribute, then we know, oh, we call this is a mug. Or alternative perspective is to see, no matter how the mug looks like, and the mug serves for the purpose of for people to pick it up and drink from it, right? So as long as it carries that kind of functional property, we said this is a mug. But these two type of characterization of the objects are actually connecting with each other. For example, in this case, think about like I show you this mug and I want to grasp the mug from the handle behind, right? So from this partially observed view. So in order to kind of pick up the mug from this view, and we need to kind of do some kind of implicit 3D reconstruction to kind of get a sense of the shape of the handle to be able to pick up the mug. and that requires some affordance understanding. And then once we pick up the mug, being able to pick up the mug from the handle, it actually confirms that there's certain 3D geometry at the location of the handle, right? So that kind of confirm the 3D reconstruction we done from the partial view. So there's a good amount of synergy between understanding the scene affordance, the functional property of the scene, as well as like the geometry of the scene. So to capture this intuition, we designed the GIGA. We try to design a unified 3D representation that encodes both the functional property and also the geometry property to encourage both affordance understanding and also like a geometry understanding. And then we want to train this unified 3D representation with multitask supervision that jointly predicts like affordance and also 3D reconstruction. So this leads to our work GIGA, that stands for grasping the implicit geometry and affordance. The first question is, what would be an ideal, like a unified 3D representation we can use to encoding the things for affordance and the geometry? So we're kind of motivated by recent success of Nuro field. You might hear the word Nuro field from the 3D contribution and graphics community. What is that? Your Nuro field is in essence a coordinate-based neural network that maps like 3D coordinates like X, Y, Z to some quantity at that location. And this quantity can be the binary occupancy, the science distance function of blah, blah, blah. And why this is a good idea to map coordinate to some 3D quantity is that it allows us to encode the object information or scene information in this deep and like a parameterized neural network parameters. And then, so that gives us a smooth and continuous encoding of the 3D scene. And this is this way, and we can leverage one of the kind of best property of neural network for interpolation, right? So once we train this neural field, and we can query arbitrary locations, like the quantity at arbitrary locations beyond at the points that we trained that on. And also because that this is a end-to-end trained neural network, so it can be plugged in as part of a bigger network and trained with like a rich source of supervision with end-to-end learning. And concretely, how we design the architecture is start with like input TSDF. TSDF is a truncated science distance function that you can get from the depth camera of the robot. And we first perform 3D convolution to map this raw TSDF into the structured feature grid. And then we actually like project this feature grid to 3 feature planes along the XYZ. Using this, we given a query coordinate like XYZ, we can calculate a local feature through feature pooling and the interpolation. Using this local feature and graph center, and we can pass that into an implicit function like an affordance decoder to decode the grasp affordance in the form of a grasp quality at the location, as well as like the corresponding grasp grip orientation. Similarly, given a query point x prime, y prime, z prime, we can decode the 3D quantity here, like the binary occupancy at that location, so that we can perform implicit 3D reconstruction. Using this implicit function, we can extract the 3D mesh from like a classic algorithm, like Marching cube.
I have a question.
Yes.
So is this structured feature grid in a canonical coordinate?
This is in the word coordinates. Like we have this depth camera, and we first like kind of take multiple views of the workspace, and then we fuse them together.
So is there some, for example, a sigma could have different rotations and translations? Do you offset that here? Or
We don't.
Is that
We don't.
a known factor?
We don't know the pose of the.
You don't know.
We don't know the pose of the mug. So yeah.
Okay.
Mhm. All right. So, like one question is like where is the supervision from, right? So remember that we have 2 types of loss function. One is affordance prediction, one is the 3D reconstruction. So for affordance, we take a self-supervised procedure, and in simulation we can dump like a large scale like 3D like synthetic objects, and then we can sample random grasp of. And you can imagine some grasp will lead to success, other will lead to failure, right? So this will give us like a positive and negative set of grasp training data and to train the affordance model. And because this is in simulation, we have access to the underlying 3D mesh, so we can train the like 3D reconstruction branch with the 3D ground truths. So before I show you a couple of the quantitative results, and I just want to give you a qualitative sense of how this model works. And typically, so doing real robot evaluation is really hard, and I'm sure that you guys know that like so. It's hard to do real testing with a real car, right? So like to get like a quantitative sense of the performance. So that's also true for the manipulation domain. So what I usually do to encourage my students is like to show me an uncut video of 10 minutes of continuous execution. You keep resetting the environment and make sure that you kind of reduce your bias of resetting the environment and in a systematic way, and then just like try out like evaluate the robustness of the system in this repetitive trials, right? So here you see 10 minutes non-stop execution, and most of the grasp are successful, and sometimes it failed to grasp the first shot, and then it was able to kind of pick up the objects in a second trial. And quantitatively, we found that compared to prior studies, like using this kind of like a structured implicit neural recognition or neural fields, and it was able to learn like a significantly better grasp quality. And also we compare a updated version of our model, which is like the green bar versus like the yellow bar. We show that by like a multitask learning and training this 3D representation to encode both geometry and affordance, it encourage like the performance for improve the performance of grasp prediction. And also because that we are using this neural field representation, we can query the potential grasp centers as like a higher resolution beyond like how we train the model, right? And then that allows us to even pick up like a higher quality grasp samples, so that we see that by using this trained model and to sample like the grasp candidates more densely, it leads to an additional boost of performance. So that shows the benefit of using this neural field representation. And because that we are using this smooth and continuous representation that's coordinated with coordinate-based neural network, so we can query the coordinate densely over the things. That allows us to map the 3D thing to this kind of a dense 3D heat map of affordance, right? So like here you see the red parts and means like the regions with high affordance score, and the gray part means like the regions with low affordance score. So we see that our model was able to generate like a more diverse and high quality grasp, especially in those occluded regions. And empirically, we found that by doing 3D reconstruction along with affordance learning, it was able to perform better in occlusion reasoning. So in these two examples, we see that the baseline model, the baseline model failed to grasp the tall objects in two trials, but like in our case, it learns to first pick up like the small object from behind, so that it incurred less collision, so that it was able to successfully declutter the entire thing. Okay, any questions there?
Input of this is the depth map, or this is RGB?
This is only using depth. Yeah, and the reason we use depth is we want to narrow the reality gap, and simulating depth sensor and adding the proper noise, and it transfer from sim to real out of box. But like so, doing photorealistic rendering, generating RGB makes it harder to transfer the grasping model. And for this case, all we want is like to pick up the object and like do sorting, right? So we don't really care too much about the semantics of the object. So RGB is not used here. But yeah, so I can imagine other problems. RGB actually provides very important semantic information. For that, we do need to consider RGB, and which is actually next work to do that. Okay.
So this is using like a Kinect kind of.
This is a real sense camera, and if you look closely, there was a wrist mount camera here. kind of as the robot arm moves and like the camera moves and like accordingly. Yeah, so this is using RealSense 435 for short range sensing. Yeah.
Do you understand correctly that for this, you don't need to segment individual objects?
We don't need to, yeah. That's because like you might wonder, in that case, how is the model figure out like so it needs to graph the top object first, or how does it even know like so what is like the objects? But that's like the magic coming from the self-supervised learning procedure, right? So if if the top object was somehow occluded or you cannot pick it, so it will incur graph failure in the kind of self-supervised data collection stage. So the model will figure out like so whether it needs to segment objects and like so in that case which object should be decluttered first. Yeah. All right. So here I showed grasping, which is pretty simple settings, and it's all about like a static visual understanding. I look at like a point cloud of the static things, and then I predict like the grasp point of that thing, right? And then like so next after you pick up the object and you rerun the model. So it's all about like static reasoning of from a single visual observation. But many real world manipulation tasks or driving tasks, it requires us to reason a sequence of actions over time, right? So for that, as a next step, we move from like a grasping to manipulation. Concretely, we look at like the task of a goal conditional manipulation of a deformable object. For example, this teddy bear, and we want to figure out like a sequence of actions that move this deformable object from its initial position to the goal state. And for that, we need to kind of look at the things from RGBD observation. In this case, like the semantic information, the texture and actually matters, and for determining the action sequences, and like the goal is to find what is the optimal action sequence, like to kind of change the environments to reach the goal states. And we are taking a model-based approach that we first want to learn a forward dynamics model. That's the conditional actions. Once we learned this forward dynamics model, we can use this with model-based control methods for planning the action sequence. So the idea is very similar to what we have in GIGA, right? So we still use the structured implicit neural representations or the neural fields, and this leads to the word ACID, which stands for action conditional implicit dynamics. That where the key idea is still learn this shared unified 3D representation that is capable of predicting different data modality or like a multiple different 3D vision tasks. So we look at the RGBD observation of the workspace and we predict the occupancy field, which is similar to the 3D reconstruction GIGA, and try to reconstruct the 3D shape from the partial observation. And also we calculate a corresponding field. So this is important for us to reason about like deformation over time. So we want to kind of establish the point-wise correspondence of the 3D shape, like under all kinds of deformation. And to reason about dynamics, we also condition the input actions. We want to try to predict a 3D scene flow. Basically, what is the kind of the movement of individual points over time, given the current observation and action.
Yeah, one question. So condition on the action, you're predicting scene flow in this neural field space, is that?
In the neural field space. So the neural field maps quantity, like a XYZ coordinates to some quantity, right? So in this case, is the flow vector at that location.
I see. So before it was like occupancy, now it's a flow vector.
It's a flow vector,
Okay,
but we are predicting occupancy together, right? So we are predicting these three quantities together.
Got it. Okay.
Yeah. And using this approach, and we can kind of grab like different output from the models for model predictive control. And concretely, what we do is we sample action sequence with the occupancy field. We can keep track of the object and how it deforms over time by running the occupancy field. And then we also need some kind of measurement of the quality of the action sequence, right? So for that, and we evaluate the action sequence using the correspondence in the flow field. Basically, what we do is we compare the predicted 3D shape after a sequence of actions with the targeted shape, and then we calculate some kind of distance metric. And using that, we select the best action sequence, execute the first action in that sequence, and then we plan. So that's the classic model predictor control loop. So using this, and we're able to kind of like deploy this system to like manipulate deformable plush toys and in the real world. And so none of these objects are like the model was trained in simulation. None of these objects are ever seen in simulation. They come with a different morphology and different physical properties. And through like some careful randomization, both in terms of visual and also in terms of dynamics, that was able to transfer to the real world objects like sim to real in zero shot.
So I mean, like previously, like in your like RGB, so those are all inside simulation. Like you have like some random background image and also.
Yeah. So this is using RGBD, right? So, and like the way we are able to transfer the RGB is through like aggressive domain randomization. We change the lighting, we change like the brightness, and we change like a light placement of the light, and we're able to like generate a large scale data sets by kind of running parallel copy of simulation on GPU. And then by training on these diverse data sources, it was able to narrow down the domain gap. I think there's still a quite sizable domain gap. I would have to admit that, like, so the real robot deployment still does not match the performance of simulation. But we can see that through this randomization, it was able to close like good amount of like a domain gap, reality gap between simulation and the real world.
In this case, how are you solving the MPC objective? Like, are you using like CEM or like other sampling-based techniques? Or?
Yeah, so I mean, the naive approach is just to do random sampling, but as you can imagine, this is a pretty big like action space and a continuous like 6-stop gripper placement, and so we need to use some kind of CEM cross entropy with this method, like to kind of gradually narrow down the search space and the like more promising actions.
Got it.
Right. Okay, so that's kind of two applications of this like neural field representations for actions and for that learn from interactions. So after this two work, we kind of want to take a step further to think about the problem. Can we build more kind of invariant models of objects that we can use in simulation, or like we can spawn that in physical simulation and then train robot with those models of object, and then maybe kind of take that back to the real world. All right, so why do we need interactions to build object models? So if I kind of show you these two objects, you can imagine if you pull the door, where the door, how the door will move, right? So, well, can probably make some educated guess, like how the door will move based on your prior, but it's only until that you see interact with the object and move them, and you kind of confirm like whether your guess is correct. So this interaction creates this like a sensory stimuli that help us like build better and more accurate models of objects. So overall, so a lot of our research look at the problem of how do we kind of look at the observing and interacting physical world in the real world, in the universe, and then create like this virtual copy of this physical object, which we call the digital twin, in the simulated environments for interactions and for robot learning, and using the fashionable languages from universe to the metaverse. So that leads to the work Ditto that we explore in for articulated object, where the idea again is like same idea of like a joint path training, like with like a multiple different supervisions to predict different quantities and using some kind of structured 3D representations. So in that case, because we want to infer the like articulation properties and resolve the ambiguities of the articulation properties. So what we do is like we input 2 frames of the same object before and after interaction. We pass that through Ditto to predict like quantity, like a part level segmentation, their part level geometry, and their articulation parameters. So one of the key challenge of 3D computer vision in that case is when you have data aggregated from multiple views or across time, always correspondence is a challenge, right? So like the pioneering in vision, Takeo Kanade said like, so what are the hardest three problems in 3D vision? Correspondence, right? So here, like we see this in asset, like learning the correspondence field is hardest to establish the relationship of the deformable object over time as they deform and change configuration. Similar story here, that one of the key challenge is to understand the association of the points and the 2-point cause of the same objects under the articulated motion. And so what we do is, I'm not going to go too deep into the architectural design, but the key principle is like to establish the association and the correspondence. And concretely, what we do is like we first learn some per point embeddings on this point cloud, and then what we use something like cross attention mechanism similar to the kind of key value pairs used in the transformer architecture to kind of establish the kind of point to point correspondence. And then after we learn this kind of fused point features, and we pass through this neural field decoders and to output like the occupancy probability for 3D reconstruction, as well as like a mobile probability for part segmentation, and also like the joint parameters. So again, just a kind of video to show you intuitively how this works. And if first collect data, you see there was a wrist mount camera on top of the gripper to collect the data, and then we collect the point cloud data before and after interacting with the object, and pass through Ditto to generate this like interactive digital twin. It have the part level segmentation as well as like the articulation parameter. Because that we apply this to a variety of object categories, and the model does not know the category beforehand, and also it works on kind of two type of articulation, like the revolute versus like prismatic joints. And why we like simulation is that simulation is cheap, is safe, and is scalable, right? So we can kind of train our model and debug and prototype our model without the worry of kind of deploying on the physical hardware and break the robot. So so that this kind of paradigm enables this kind of simulation in the loop learning, that we can go from real world observations like interacting with the faucet and collecting the real world observations of like point cloud observation of the thing, and then using Ditto to create this interactive 3D model that we can just directly port in a physical simulator. Here, this is a Majoko, like a commonly used in manipulation domain. So we can train our robotic model using reinforcement learning, imitation learning to kind of play with and interacting with this simulated copy of the real object. And because that this simulated copy matches the real world objects, so it narrows down the reality gap, so that it allows us to transfer the learned policy back to the real world for real world execution. And then the real world manipulation, again, like creates new sensory stimuli for us to kind of keep refine our modeling of the simulated object, right? So this in general, the paradigm of kind of using real world data for creating realistic simulation and then taking it back to the real world to further collect data. Very promising paradigm for manipulation, as well as like many autonomous driving scenarios have been also looking at kind of how do we build good simulation from driving logs, for example.
So
yeah,
you mean like this is to you build this Ditto model, and then using the Ditto model to sample from this model to get training data to train in simulation?
Yeah, so this is not a generative model per se, right? So we're not trying to learn the distribution of or the space of possible faucets, right? So this is like just a one-to-one copy of that exact faucet. So it's like we are kind of virtualizing the object and to create an exact copy of the same object, but we want to make sure that's simulatable. But to be able to simulate that object, we need to know the articulation, we need to know the physical properties, we need to know the part decomposition, so that we can kind of define so that we can kind of describe or define the object in URDF or some kind of 3D formats that we can import in physical simulation. Right, so that's the idea. Yeah.
Can you somehow infer, like, it's maybe correspondences or something? For example, so that this specific part can be rotated in this like plane, and this specific part can be rotated in a different plane, given like using only simulations. Or we just need to this prior information in order to be fed into this simulation.
Sorry, what by correspondence you mean correspondence of what?
No, maybe yes, not the right word, not just correspondence, just yes, using the only observation, can we somehow infer the specific type of the motion that can be allowable for the specific part?
I see. Yeah, so that's like after we create this object, so like that's where the learning happens. Like, so the learning, what we want to do is like to associate the right kind of manipulation actions like with like the physical objects, and we don't want to do that in real world because that requires a lot of exploration. Many of the exploration are dangerous, like so or risk sensitive. So that's why we want to kind of like perform this exploratory actions in simulation, and such that we know like so for this kind of particular objects or like articulation property, what would be the like a proper actions to interact with them.
But in this case, we can use it as sort of generative model. For example, if you know like the specific types of the motions that can be applied to the specific parts, so we can just like rotate by any angle or something and just like
Yeah. So here, like, so we are kind of looking at the problem of like manipulating specific objects. But if there's like enough patterns, like if you have a large like a data set of like articulate objects, and you kind of train this model to manipulate kind of them, you can probably like distill some like a common or like consistent patterns, and so that like when you have a new object, you can do some analogical reasoning, right? So you can like so that it knows how to manipulate this object by transferring your part experience. I think that's a good research experience to explore. So now not only you establish correspondence on kind of geometry, but also kind of through the correspondence of the 3D shapes, you can transfer the actions or manipulation behavior as well. Yeah. Great. So that's kind of the first part of the talk. I kind of talk like about this frameworks and from GIGA and ACID and Ditto, like so on kind of learning actionable visual representations. Just want to kind of summarize like what are the kind of properties of this like visual representations like we think is very important and in this line of work. One is that task dependent, right? So because like we are using this near field representation that can be end-to-end optimized with downstream tasks, so they directly capture task relevant information that's crucial for the downstream tasks, like for decision making, like for directly predicting and grasp affordance. And it's multimodal that we try to use this unified 3D backbone to predict a variety of 3D quantities, like including geometry, like their function property, affordance, and dynamics. And we show that there's good amount of synergy between these different predictive tasks. And by learning them together, it gives rise to more robust and generalizable representation. And we show that what we learn in 3D vision and still offers a good amount of inductive bias, right? So combining this explicitly feature grid and with this kind of implicit neural field representations allows us to scale this model in larger things, like that's different to do with like a vanilla kind of neural field representation that's commonly used like a MLP. And big question is where the supervision is from. So like we talk about like embodied interactions and the agent's own experience, like exploring the physical world, offers a good amount of training data for us to learn this actionable visual representations. So that's kind of the first part of the talk, and on state abstraction. So like moving on for the second part, I'll talk about like a action abstraction or behavior abstraction. Again, like reviewing like 3 of their work on this line. So to talk about like a behavior abstraction, the key concept behind is the notion of compositionality. Everybody is talking about compositionality these days. Like many AI and machine learning researchers ask, if you ask them, they say that well, capturing compositionality of real-world phenomena, let it be language or image, video, or like a task execution, robotic task execution, is a key to improve systematic generalization of robotic system. But what exactly is compositionality? This is a notion that has been studied for hundreds of years, actually. Like so, from like philosophy, people in like mathematics and linguistics, and they have been studying that. So where they study how the kind of meaning of the sentence emerge as the composition of a bunch of words in it. And similarly, for robotics task, if you have like a very complex task, like say preparing dinner, drawing a parallel, we can also break that down into simpler subtasks, like you need to wash dishes and cook food, and then like they can be further decomposed into even simpler behavior, like a grasp, pick, place, push. And we call this kind of bottom level behavior building block as sensorimotor skills that are grounded in raw perception, and then they are typically like a temporally extended behavior abstractions for us to we can use them as like a Lego blocks to kind of synthesize like long-term interactions. So for compositionality, and if you look at like the actually linguistic literature or like a philosophy literature, there's kind of 2 mainstream of thoughts on like how to approach compositionality. The first is called context principle, meaning that the words, they don't have their meaning in isolation, and they have their meanings as constituents of like the sentence, right? So like and it's the context actually instantiate the meaning of the word. Like the sentence here, the little yellow dog bark at the cat, and the meaning of the bark hinges on like the surrounding words. It's a dog that bark at the cat. Right, so that kind of the context really kind of endows the meanings of that word. And then on the other hand, there's the opposite, and there's this compositionality principle that tells that well, individuals have their own meaning. Like dog is dog, bark is bark, cat is cat, and when you kind of compose them together, and the meaning of the sentence is a function of the meaning of parts. So which one is more true than the other? That's still an ongoing philosophical debate, right? So it's an open question. We're not going to argue that about today. I'm going to just see how we can draw insight from these 2 principles to kind of develop a compositional approach for behavior modeling. And the first work is BUZZ, like a bottom-up discovery of sensorimotor skill, where we look at if I give you a bunch of task demonstrations, how can we extract a library of sensorimotor skills from those like demonstrations? So once we have these libraries, you can think about this as a bunch of function APIs you can call, and you can train a meta controller to invoke these APIs, like when you want to kind of synthesize some behaviors. And we want to have this very practical method that can work on real robots. So we want to kind of take the minimalistic assumptions, like it does not require any temporal annotations of the demonstrations, and also the skill should work that are grounded on raw sensory data. So the first step to approach this problem of skill discovery is like to build some kind of hierarchical representation of a task demonstration trajectory. So looking at this long trajectory, and then we can kind of recursively group the shorter like temporal segments into bigger ones. And the way we do that is by iteratively find the 2 most similar temporal segments and then merge them into one. So this is called hierarchical agglomerative clustering. And then
how do you define the similarity?
Yeah. So I'm gonna see. So the similarity here is actually defined by some multi-sensory cues. So we look at like the onboard sensor, like the vision data, and it's also like the tactile and haptics data. And so based on the correlations between these sensors, and then we kind of get a sense of like how similar these two segments are. So does it make sense like to use? Why do we use multimodal rather than only relies on visual features? Is that sometimes in manipulation task, the visual data might not change much, but actually the subtasks change a lot. Think like inserting a tag into a hole. Right? So at the insertion phase, probably the vision does not change much, but like before and after insertion, the haptics data really changed like drastically. So based on the insertion behavior. Right? So that's why we use this kind of multi-sensory statistic to compute some signature of temporal segments. We use them to group them together. And after we discover this like hierarchical temporal segments, we can just find like the consistent patterns, recurrent patterns from these temporal segments, and then we use them as like the training set for scales. Just to illustrate this high level idea, and we have a bunch of temporal segments. We compute this signature of each temporal segments, using the kind of multimodal representation learning, and we have a bunch of demonstrations collected from all kinds of diverse tasks, and we map each of the segments like from the hierarchical representation to this latent space of behavior. Right? So for each temporal segment, we map this to a latent embedding in the feature space, and we can perform a clustering steps to group these points together into K clusters, and here this K clusters would serve as the training data for K different scales, and we can use this to train a scale with imitation learning algorithm. And once we learn this K scales, we can train a metacontroller again with some low conditional imitation learning objective to invoke the scale at each step by predicting the scale index that like select the scale and also a subgoal that instantiate how we should execute the scale. So this has been kind of a quite effective approach to handle like a long horizon task. This is some kind of simplified cooking task, and we show that only by training on 30-minute demonstrations, and it was able to effectively solve the task. Where like if you only use a flat policy without any kind of hierarchical modeling, and it struggles to solve. And some kind of interesting observations we have is like by kind of extracting these skills, not on a specific task, but like a diverse range of prior data, and it allows us to learn more generalizable and reusable, improve the reusability of the skill, right? So we show that by extracting this skill from multi-task demonstration, I actually improve the success of like executing individual tasks. And also we show that these skills are can be used and transferred to novel tasks. And so the way we use it is like by freezing the skills and the retraining only the metacontroller on how do we invoke those skills, like to kind of piece them together for solving like a novel instance of the task. And because I said like, so we want to make this task practical, it does not rely on temporal annotations, it works ground up from like raw perception, so we can kind of deploy this to a real robot for kind of this kind of cooking type of task. And this is trained on demonstration collected, about like a 50 demonstration collected in half an hour to kind of perform this reasonably hard multi-step task. Okay, question, yes.
So does this feature space embedding highly dependent on the scenes? So for example, it's a cooking scene, if you change it to like washing something, then like
Yes,
it might
yeah.
completely has a domain difference.
Yeah, it is. So for this, we are collecting a diverse range of tasks, but in that same workspace, right? You can imagine. So to really take this method to the next level, we need to still increase the diversity of data. So, yeah, ideally we should like collect this in thousands of different kitchens, everybody's kitchen, and they are doing kind of millions of different tasks, right? So like they really can like scale this up, this method to, but right now for this method is only applied to a fixed environment. But with kind of object variety, but not with kind of environment
I see.
variety. Yeah. Okay,
So
that's a good question.
you seems to show like by decomposing this to like hierarchical task, you can be much better than behavior cloning.
Mhm.
But there's also work on like implicit behavior cloning, right? Like
Yes.
where you use generate modeling or EBMs, and then
Yeah.
it seems to perform much better in closed loop kind of setting. Why is it like the pure behavior cloning in your case show bad performance, but if you're like using a little bit more advanced like implicit behavior cloning, would that be performing better?
Yeah, so like why people like implicit means that you are learning a function of x, y rather than you learn a function y equal fx, right? So y is a better idea because in a lot of this manipulation task, its contact reach is like a non-smooth kind of like a very you are dealing with a very discontinuous or like a non-smooth dynamics function. So neural network does not really like that. Neural network like more continuous and smooth output. So that's why you learn this implicit function of f, x, y is better to deal with those kind of non-smooth changes in the kind of optimization landscape. But in this case, we are taking a different strategy, right? So we are dealing with like those non-smooth dynamics, but we kind of abstract them away using low-level skills, so that when you train the high-level like controller, you are calling skills rather than you are outputting the low-level motor actions. So so in some sense, some of the kind of the challenge of like modeling dealing with like the low-level dynamics was abstract way through our skill abstraction. But yeah, like that kind of implicit BC model can still be applied in principle with this approach. Is that for implicit BC, it has its own challenge. Talking about the action evaluation, right? So so I think also still idea needs to be combined, especially for implicit BC. It's hard to scale that up to very high dimensional action space. Like in this case, where you're just using kind of drawn space controller with like maybe like 10 degree of freedom, right? So it might not be it might be hard to apply implicit BC directly. Yeah, that's a good question. So just we just want to move forward because kind of time is running up, and we can kind of open up discussion. I do have more time afterward. So I talk about like it kind of resonates with like the context principle, which we first have the sentence, then we discover the words, right? So we have the task demonstrations, and we try to extract the constituents from that kind of task as skills. The opposite direction is like, what if we have a predefined set of skills, right? So like, can we kind of learn the function that compose them together to kind of model long-term behavior? That's what another direction we explore in the work Maple. Here we look at like, what if we are given a set of primitive skills? You can imagine these are like a manipulation primitive, but similar things you can apply to driving scenario as well. We call this heterogeneous because these skills might operate at different temporal resolution, and they take like different arguments to instantiate their execution, like reach, grasp, push. Why do we like these skills, right? Because like in the robotics community, there's like decades of research like dedicated to building this kind of special purpose behaviors like grasping, motion planning, dynamic movement primitives, etc. So this model are very well understood. They have a strong generalization property, and also like they often have good performance guarantee compared to just end-to-end learning method. So we want to kind of see if we can make use of these methods. But one special consideration we have is if you only have like a few skills, like 4 or 5 or 6, it might not be able to express all possible robotic behaviors, right? So so that's why we added a special skill called atomic primitive. That is essentially the low-level motor action, like the reinforcement learning algorithm typically use to just fill in the gap in case like some behavior cannot be expressed by this like a finite set of skills. So when you use reinforcement learning method with the skill library, you kind of change the underlying action space with this skill library by selecting a primitive and also predict the parameter that can instantiate the execution. So that's the high level idea. I'm not going to get into detail into the model design, but it's some kind of hierarchical software actual critical model to be able to train with this hybrid action space. We have some discrete actions to select which skill to use, and also we have some continuous action to output the skill parameter.
So you mean like you have this set of primitives, you select one of those, and you also ask the RL model to predict some.
The parameter, like for grasping, is the grasp center and the gripper orientation. Right? So that's the continuous part.
And you are just using the reward and using RL objective
Yes,
to
yeah.
run all those.
Yes.
together. Okay.
Yeah.
Is it very tricky? I mean, like if you just select, maybe the reward might be easier to tune, but if you also need to predict this continuous parameter, like your reward tuning might be harder.
So this is in a task reward. We do have something called affordance reward to encourage the parameter to be more meaningful. See, they makes meaningful changes to the object, right? So, but for that, we kind of encourage the robot to select the parameter to make physical interaction with the object. So there are some kind of auxiliary involved, auxiliary rewards we use to facilitate exploration. But it's true that doing exploration in the kind of skill parameter spaces can be challenging if you only use a task reward. Yeah, so we kind of tried out a variety of manipulation tasks and compare with a bunch of baselines. Of course, the most basics is only used in the atomic action, but I thought the most interesting is compared to our self baseline that does not include the atomic action. So we show that actually going from the Maple non-atomic to our final model, there was an 11% boost because for some tasks, we cannot be modeled with only the skills in our skill library without kind of using the low level action. Just kind of to show you a concrete example, like the pack insertion task I mentioned earlier, right? So that's some tasks that the last phase of the insertion task requires some precise alignment of the pack, and they have kind of wedge the pack into the hole. So that's some kind of dexterous and the contact reach manipulation. Really hard to model by a motion planner or kind of dynamic movement primitive. So for that, we see that Maple succeed for doing this task by relying on the atomic actions at the last part of the insertion phase of the task.
Just curious, how many to complete a task, how many basic skills you usually use to understand how fine grained?
So this is exactly the skill library we use. We have this.
So for example, how many invocations you need to make to that?
Okay,
How
that's
fine grained you broke down into pieces?
Yeah, that's a good question. So I have a kind of hidden slice, but let me see how can I show you. Yeah, so for that, we actually try that out, right? So we see if we execute the task and we can look at what are the skills that are selected and for doing the task, and then that actually allows us to understand the compositionality of the task. So we have something called a skill sketch. Basically, each step corresponding to one function call of that skills. You can see for lift is pretty easy. One grasp and one reach and then one grasp. And there are some kind of pick and place tasks that you have a pretty consistent skill sketch, but some tasks are less compositional, like the last one, the pack insertion, like the gray box are the atomic actions, right? So that means that given under this skill library and you need to rely on a lot of this atomic action, then that can raise an interesting question. Can we, using this skill sketch, can we kind of continue to discover new skills and add them to the skill library so that the non-compositional task becomes more compositional as you grow the skill library? Yeah. Yes.
On that. Sorry. Good. Are the other tasks, skills, I guess, expressible as an atomic, or those are disjoint?
They can be expressed as atomic. so autonomic action is express anything the robot can do, right? So the grasp and the reach and the push are just a sequence of atomic actions. So the atomic is like the kind of the bare metal, the lowest level action API you can use.
So what's the benefit of the others then? Is this just, it makes it easier to?
This is reinforcement learning. So one of the key challenges is exploration, right? So if you want to solve a task like a tag insertion or wiping with only atomic action, it requires hundreds of steps. But using the skills, and it has the temporal abstraction, so you can solve that in like a 10, 20 steps. So when you use the skills to do exploration, you can do a lot more structured exploration.
It's complexity reduction because you know that these are those.
Yeah.
Interpretive tools.
I guess you're basically just effectively reducing the time horizon of your problem. But
It is.
I guess one question related, or I was curious, like in the peg insertion, are all those like atomic action, just like the alignment at the end, like just like once you've already reached, like just like trying to align with the peg itself. Oh, okay.
Yeah, it is. It is.
I have a question.
Yeah.
Are you forcing like each of these primitives to execute to completion, or do you have like?
There was a timeout. If they failed, then there was. If
Okay, so there's no like automatic like learned way to say, oh, this current primitive is.
there's a stop function, and also there was a timeout. So if you exceed like a 15 or 30 steps, and if you still haven't grasped the object, then like you hand over to the high level controller. Now tell me what's the next skill to do. Yeah.
Are there any like preconditions that have to be satisfied before you can call specific skills?
That's like the high level policy's job to figure out what like what the next skill to call, right? So we don't have the precondition explicitly like a planner, but it's the high level policy job to learn that implicitly.
I see, but in principle, it could call grasp at any point.
In principle, I can.
Okay.
Yeah. But it's a good, I think it's a good direction to explore. Is like how do we learn this precondition so that we can mask out those skills that are not possible to execute, right? So here we're just exposing the entire skill action space to the high level controller. Yeah. And I just thought so the benefit of using skill is like the temporal abstraction offered so that you can do more structured exploration more efficiently. And also another is it can kind of abstract away a lot of the low level dynamics mismatch, right? So like now if you are using a motion planner from sim to real, it transfers so much easier than transferring the low level motor action. So that allows us to kind of train the model with skill in the digital twin. We talk about it in Ditto, and then get this zero shot transfer to the real world by using the skill abstraction. And so for how this transfer is like we have a post estimator to detect the 3D bounding box of objects, and then we train the policy on that detected 3D bounding box. And transferring a 3D detector from sim to real is a lot easier than transferring an end-to-end trained policy with good amount of randomization, domain randomization.
Because now your actions like this primitives and then
Yes, and domain randomization for vision is a lot easier than domain randomization for dynamics. So that's here where we do how we do the transfer. Okay, so that's kind of these two main work I want to show, and I talk about state abstraction, then action abstraction. The natural question is can we kind of just incorporate the state abstraction into skills? And then when kind of people talk about imitation learning, they kind of always feels it's not as kind of general as reinforcement learning because of the covariantship and issues with kind of distribution mismatch, right? So I think incorporating the proper state abstraction is the way to kind of make this imitation learning method generalized across beyond the training distribution. So we have been looking at a variety of ways of improving generalization for imitation learning algorithms. So one particular kind of direction we are quite excited is object-centric representation learning. So how can we baking the object acquirers, let them policy aware of the object and their interactions. And this is some unpublished work, but I thought it's just to include here to show you some of the kind of preliminary results in this direction, where we look at the raw visual observations and we use a open vocabulary object detector to generate like object proposals. And this is trained on some open vocabulary data set called DITIC. The model is called DITIC. And it got this like a bounding box candidates, and we can use some transformer models and to kind of reason about their pairwise relationships and form some object-centric representation. And then this representation can be passed to the imitation learner that we have been talking about so far, right? So to output the robot action. And this kind of object-centric inductive bias has been showing quite effective in learning robust like policies. So here, this is a real-time example of like we are kind of training our robot to make coffee for the sleepy graduate students in the lab. This is a one skill trained on 50 demonstrations, right? You can see that it learns this kind of robust behavior, and it learns to retry how to close the cap and press the button all in one shot using the power of the skill abstraction offered by the offered by the object proposals. Okay, so this is this, and that kind of concludes the second part. I talk about how do we do like behavior abstraction from like diverse prior data. We build hierarchical model that make use of this behavior primitive as APIs, and then like so using this, we can scaffold long horizon robotic tasks. And the last, I can show you some initial results of using object-centric priors as a skill abstraction for kind of imitation learning. Yes.
A question about the open vocabulary object detector. What is it?
Okay, yeah, so that is just like CLEAP model that are trained on natural language descriptions of objects rather than
but you need to provide some sort of description, text description.
Yes. So that's trained on some kind of internet skill kind of data sets.
Yeah, I know. But how do you like detect the specific object on this scene? You need to provide text description like mug, something here.
Right. So that's the kind of appeal of this method, that we don't need to kind of annotate the bounding box of those objects and detect those objects. So what we do is like we just fire this object detector, and then we get the top K bounding box. Like typically, if you generate like a 20 to 30 bounding box, it already have a very good recall of the object interest in this thing. It was able to kind of like have a box crop out like the coffee machine, crop the mug, crop out the whatever a button, and then you just let the network figure out what are the objects that are relevant. All right, so when you train with the imitation learning loss, the action tells you which object I should be focusing on, which bounding box are garbage we should discard, which object I should be picking on learning features to output the actions. All right, so that's how it works, and we are not kind of telling the model like which object you should focus on in this case.
I think the open vocabulary, maybe Professor Wang, last time he presents some work. Is that from? I mean, I think like Xiaolong Wang.
This is from Facebook, and there's like many work on like kind of open vocabulary detection, but this is one of it called DITIC. Yeah, and like the bounding box here is exactly the bounding box coming from the. This is a real data, not just kind of a proper concept. So you can see like, yeah, it has been getting like some impressive results. It's like this object detector clip based and generating good bounding box and generating good like text descriptions of the objects.
So when you say you use that detector to get you the bounding boxes, does it also tell you some sort of classification of what that object is?
It gives us the actual language description, and you can like maybe you can pass this bounding box to clip and to you generate like a natural language.
But do you pass that on to your model?
We don't.
So you only look at the bounding box, but it doesn't care that this is a
we get the bounding box. We extract some visual feature from the bounding box. We don't use the natural language part. Yeah.
So basically, this prior is basically telling the model where to focus when seeing the demonstration.
Yeah. So this is just giving me as much object as you can recognize, and then like the imitation learner will kind of pick on the right relevant object and then like so output action from based on that. Yeah.
Does it give some information about relationships between the objects? Like
That's where the transformer is in action, right? So we want to have this cross attention over the. We treat each bounding box as a token, and we send them like sequentially to a transformer. But like, we are using this cross attention mechanisms to establish relationships across the object. Yeah.
What do you think about, I mean, it seems like you use some detection to extract into bounding box or into patches, and then you try to use that to learn. What is your view like end-to-end? What if just, build a simulator and then it's gonna just, encode all the image as input and then the policy?
Yeah, I mean, we try to actually like train the detector either from scratch, and that's by using the network, or like we fine tune the detector together with like the policy. But the thing is, like, it has not been giving us good performance because like we only have 30 demonstration at the end of the day, right? So like the supervision from the action, the final downstream task is too sparse for us to learn or improve the detector performance.
But what if, for example, in some scene level, like the whole image level embedding, the all information is already encoded, and we don't need just to extract in the beginning, then to feed. Can we have like a good representation of the whole?
The whole image. Yeah. So actually, there are something that I kind of because I would say 3 the rock is there was a global image token as well, because you actually need to kind of see the kind of overall holistic view of the entire thing to get a sense where the hell all the objects are. Right? So in addition to the object token, there was actually a global context token feeding into that as well. But only using the object global token is not enough. That's like just what like a feed forward imitation learning model does, right? So like really the kind of the power of this method comes from like using object as tokens, right? So they kind of like using the so they can understand the individual entities that are present in the thing and also read about their relationships.
Somehow to help. We need somehow to help, like this global representation. We need to provide also like local representations.
Yes. We need this global holistic view and also more local object level information.
One question related to that, like, I guess this is maybe like a more general question, but I guess here you're like, you're learning these intermediate representations and then feeding them into your policy.
Yeah.
But you could imagine like alternatively too, you could just like, learn all these as like auxiliary losses and then just, feed your policy like the original, like just like the representation that like results from all these auxiliary losses that you're adding on top. Do you have thoughts on like what would make more sense in general and why?
Yeah. So typically, I mean, like, so when you do the auxiliary loss, like you need some kind of supervision, like come from the end task. But in this case, it's like so the end task only provides sparse data points, like 30 demonstration. You don't really have the bounding box of the object, right? So for you to train the detectors in the target domain. So that's why we pre-train them like in the like an internet scale data. If you have really abundance of data, so that's where actually I think like the robotics community has been looking at like, so how do we kind of replicate the success of foundation models in vision and language to robotics? So we need this diverse data pre-trained, but where the data from, right? So like and how do we pre-train them, like what do the right supervision? I mean, those are kind of interesting questions to explore. But yeah, so for this, like we kind of leverage the internet scale data, but it's not necessarily in the kind of manipulation workspace. But they give pretty decent bounding box, and I should say.
I have a question. So this kind of reminds me of like how people used to have scene graphs for like vision language
Mhm.
tasks. So like from those domain, like the scene graph is more like modeling the objects and their spatial relationship, for example, because that's what they focus on. But in our case, is there any chance to use scene graphs to model like how the objects could be interacted by the robot?
Yeah. Definitely. So in this case, it's kind of a scene graph, although like so.
Just with only the nodes without
Yeah,
the
yeah.
edges.
I mean, the edges and they don't have like the semantic relationship like the in vision language people care about, like man riding a horse, like a person walking on beach, something like that. But we don't have that kind of a semantic relation to describe the kind of the like subject object into like relations. But with some kind of relational reasoning is needed. So that's why we have this kind of cross attention mechanism. It's just that it was unclear. So how the model make use of this relationship. So it's better off just kind of hand this over to the policy learners, so to let it figure out like so what kind of relational reasoning is needed.
Maybe the order in which these objects needs to be like touched or something.
Yeah, or like the more like
Those-
the interactions.
Mhm.
Like maybe two objects could be interacted together, like the coffee capsule could be inserted.
Yeah.
Or and they could prune it to be very sparse.
Yeah, we don't enforce sparsity, but like so in the paper that we are actually going to release this paper about in 2 weeks, and we have some kind of visualization on like the strengths of the kind of cross attention, right? So and then you can see on each stage like which paths like which kind of relational edges are kind of activated, like when you calculate the kind of the key value, like a key and a query pair. Right? So that's some kind of indication of like which relation is activated, like so for determining the actions. But as I said, we don't have that kind of semantic semantic relation predictions as in singular.
So do you end up with sparse connections even though you don't enforce it, or is it not the case?
It's not the case. Yeah,
Oh.
and also not all kind of strong connections are interpretable. I just say, yeah. Sometimes you can kind of look at this edges. Oh, you find this makes sense, right? So kind of try to kind of interpret. Like the picking the mug, and then like so the mug was kind of and the hole, or like the holder cup holder got activated. But like sometimes like you see the strong edges that does not make sense to human. So yeah, I think like so it needs some further investigation for sure. Yeah, and actually, if there's like a scene graph type of annotation, it would be a good source of like auxiliary task that would probably be able to use as a regularization term for the attentions, so that we kind of get rid of those various dependencies. But in this case, we don't have that kind of regularization, right? So it's all relying on the action supervision for us to figure out like so. Yeah.
I see.
Very complex. I would say here it's very complex task to do sort of markup for single
Yeah.
just because it's expensive.
Right. Yeah. So I think that's actually all I want to talk about this 6 like works. But in general, what we are excited is like looking at like so how AI architecture of robot autonomy emerged. I talked about like so we want to have the modularity and the composition in place, but also modularity is what exactly the classic robotics pipeline have done, right? So like the perception people work on perception, they map that to some physical states, they do post estimation, and then the planning people work on motion planning, assuming ground truth physical state, and then they pass them to the control people, and then like who did PID, and then like so suddenly a lot of like a machine learning, deep learning community look at like the end-to-end approach that directly maps from the raw sensory data to the low-level motor actions. But I think we are in this kind of transformative period that we start to look at. Like, so again, combining this engineering principles of compositionality, modularity, good abstractions, but also implementing them with learnable kind of modules, and so that actually individual modules are highly coupled together through the state and action abstraction. So like my former lab mate, like Andrew Kawasi, he said like this is software 2.0, right? So applying some of the software design principles for robotics, like so combine deep learning with principle of abstraction and the composition. We can break that down, a very complex system that will be driving all robotic manipulation into this kind of functional decomposition. Meanwhile, they can be fine-tuned and like a optimized full stack, like a full optimization and the specialization. So I talk about a lot of work on manipulation domain, but recently we've been also looking at like autonomous driving domain, in particular to cooperative perception. You have autonomous driving cars and like operate on line of sight and ego perception. You might suffer from occlusion, but if you have like network infrastructure, see from neighboring cars or like a kind of the traffic lights, and then like it enables like the augmenting views that avoids like accidents in this kind of high risk environment. So for that, we need to build a kind of sensor processing modules. We need to build like a sensor, like a fusion or like a communication modules. We need to build like a control modules, and that we can kind of implement each of these modules with highly structured deep neural network models. But in the meantime, we can jointly learn them together to for the kind of end goal. And so for that, just want to thank my students for all the wonderful work. So I get a chance to give a talk here. And yeah, I think that's all I want to see, and just want to stop here and see if there's any more questions.
I think we asked all the questions.
Yeah,
Here in the talk.
you guys have asked a lot of great questions. Yeah, I think now I have more ideas what to do next.
I hope we do.
What do you think about like safety when you try to do this self-driving?
Well, you guys are more expert than I do. I feel like, yeah. So yeah, there's like a different views of the safety, right? So like from more probabilistic notion of safety to more kind of a formal guarantees and with like a formal methods. So yeah, I think a lot of work that is missing is a good uncertainty quantification or like out of the distribution detection, know when to fail, right? So of the second order question is like how do we kind of deal with corner cases, but like first detect those failures or like the other distribution scenarios will be a first step, and looking at a good and real-time and the robust uncertainty quantification method, being able to separate epistemic uncertainty versus from aleatory uncertainty. I think that would be a very good research topics to focus on. We did some work on post-estimation, but I think a lot to be done. Using like bootstrapping and learning model ensembles, using their disagreement or kind of predicted the consistency of their predictions of model ensembles as a kind of approximate metric of uncertainty. But I think a lot more needs to be done there.
Okay, so that's like estimating some uncertainty, but also like there's also algorithm like if you use imitation learning or reinforcement learning, and how do you maybe guarantee some constraint violation, right? Do you have any thoughts on?
Well, some of the constraint can be modeled as like part of the reward function or learning objective. Right, so or are you talking about like a hard constraints?
This is the question whether they could be hard or should be hard or soft or still under the research.
I agree. Yeah.
Anyway, so let's thank Lisa.
Thank you.
Can I ask another question?
Yeah.
I also have one more question.
Yeah.
Just didn't want to drag on the.
So like going back